Before starting, I'll introduce myself. My name is Amira Lakhal. I'm an agile Java developer at Valtech. I also code in Scala in my free time. Despite coding, I'm also a running addict, and I'm happy to say that I finished my first marathon race last April in Paris. So that's me over there. If you'd like to hear some tech news, you can follow me on Twitter, and all the code of this presentation will be available on my GitHub account. I'm also one of Duchesse France leaders. Duchesse France is an association aiming to give more visibility to women with technical profile and help create vocations, new vocations. We celebrated our 6th birthday anniversary last week, so we're always looking for support from the IOT communities. Have a look on our website and follow us on Twitter. The Internet of Things. When I started doing some researches about the IoT, I was wondering when all this discussion about the IoT has started, and I found an interesting report from Cisco. The report shows the growth of population and, in the meantime, the increasing number of connected devices. And according to this report, as you see here, the IoT was born between 2008 and 2009, when the number of connected devices exceeded the number of population on Earth. So today we are about 7.2 billion people on Earth, and each one of you had at least 3 connected devices. And an estimation says that we are going to reach 50 billion of connected devices in 2020. So imagine this huge amount of network of connected devices with multiple technology, with multiple connectivity like wireless or internet. All these systems are contributing to the Internet of Things. And this system is actually capturing a huge amount of data. So we are, as we know, in the big data era. So today, if you only focus on social media users counts into billion, and each one of them can have a lot of connectivity to content. Actually, there is 10 of thousands of connection to content. So we are facing a huge amount of data. Around a lot of zettabytes of data are here now. And the challenge is to speed analyzing all this amount of data. So actually, for example, if you look to the social media, Facebook has to load 20 terabytes of photo each month. And for example, Google is processing here in each 72 minutes, 1 petabyte of data. So the challenge here will be to analyze this unstructured data, most of the time text-based data, and to have the information from this data. To do that, we have to follow some steps. First, we have to extract the information from this data, and with the extracted information, we have to gain the knowledge, and with the gained knowledge, we have to enlarge our wisdom. So the future, what we're going to have, a lot of objects and things from physical and organic world are going to merge to the digital world, allowing a nearby real-time connectivity and analysis. So when machine and products will have the intelligence to deliver us the right information anytime to any device. And when machine and products have this capability, they can help us and other devices, of course, to have the best decision, improve our services, and of course, gain time. But the reality that we are very, very far away from this goal. Actually, I have in many occasions the possibility to see the robot here, and this robot is full of sensors. But this robot is only used for doing welcoming speech in some companies and some events. Imagine instead of doing such simple things, this robot uses all these sensors and capabilities and all the data that he can capture to, for example, order your favorite drink when you're thirsty, maybe order your food, your ticket for your flight, and etc. So we are not using all the capability of the connected devices we have today. So that's why I'm only going to share my IoT world. As I told you, I'm a running addict. So to practice my activity, I use connected devices. The first one I started with is Runkeeper. It's a phone application that measures a lot of metrics while running: the distance, the speed, the calorie I consumed, etc. It was a little bit hard to do running with a phone, of course, because I have to hold each time the armband, and it wasn't really easy. So I tried the Garmin watch, my favorite devices, and with the Garmin watch, despite all the metrics I used to have with Runkeeper, I always have the real-time speed, and the heart rate measurement, etc. And I can synchronize all the data with my phone, of course. And the last one is the Withings, which is a small device that can measure all your daily footsteps to see if you have a healthy day or not. You know, we are all developers and we stay all the time in front of our computer, so this kind of device helped me to see if I did a very good activity this day or not, so I can practice at night. So today's goal will be to try to recognize physical activity with measurement coming from one sensor, which is the accelerometer. We'll try to recognize if we are jogging, walking, standing, or sitting. And this kind of measurement, for example, can be used for healthcare. Doctors can use this measurement, for example, to monitor the health status for some patients suffering from obesity and so on. And yesterday, of course, if you attended the closure keynote, there were some presentation of usage of accelerometer too. The accelerometer, as I said, measures the acceleration. So we can use it in multiple devices. Actually, it exists in all your smartphone. You have all accelerometers in your smartphone. And for example, if you like to go somewhere with Google Maps, it shows you the time to the destination, and it measures the time using the accelerometer. So each acceleration we get from the accelerometer contains 4 information: the time stamp and the forces according to 3 axes: the x-axis, the y-axis, and the z-axis. And the unit is meter per second per second. So we get a lot of acceleration during a time interval, and that's what we call a time series. So we have a lot of measurement, a successive measurement during a time interval. Here, the first step will be to get this information from our sensor. And to get the information, I have implemented a very basic Android application just to listen to the sensor. So the first screen you're seeing here, you have the welcoming screen when I can put my server URL, and then when you click to start, you switch to another screen. At the beginning, you won't see any values. We are not listening to the sensor. When you click to the start button, you can listen to our sensor. All the code is available, of course, on my GitHub account, and it's open sourced, so you can use it. So after listening to our sensor and getting the data, we have to post it through a server. And here I used a REST server, a very basic one, to get all the values and store it to my database. So the first step is to store the data. And to store the data, I chose Cassandra. Does anyone know Cassandra? Used Cassandra? A few ones. So I'll do a little reminder. Cassandra is an open source project created by Facebook in the beginning. It's open source, of course, since 2008. It has the Apache license. And Cassandra is a NoSQL database column-oriented, which tends towards distributed table abstraction type. It's very supported by DataStax, which is an American company. So you can find a lot of documentation around Cassandra. What we have to remember about Cassandra is that it is scalable, masterless, very easy to operate, and we can have a lot of data centers, so it helps us to have a continuous availability with all these multi-data centers. So here what we're going to focus to is how to store data in Cassandra. So basically, when we want to store something in Cassandra, here we try to insert user's information, the login, the name, and the age. And to store the data in Cassandra, we use the SQL here. It's a Cassandra query language, pretty similar to SQL. It's done on purpose. So here I stored my user, DuchesseFR, and with some information, which is the name and the age. So we have created a row containing 2 columns with name and age. And each column will have an auto-generated timestamp. And when we try to update the data, what happens, we're going to create a new SS table on our disk with the new information. So here we have a new SS table containing the age table, the age in a new table and a new timestamp, for example, of course, for this new column. And if we like to, for example, to delete the information about the age, what happens? We're going to create a new SS table containing a marked tombstone, which is the mark showing that we're not going to have the value anymore. So if you'd like to read the age, what happens? We're going to get the 3 assay tables to our memory, read the 3 of them, and only have the column containing the recent timestamp. In our case, it will be the last one, which is the removed timestamp. The removed, age with the recent timestamp. So as you see, in Cassandra, when you write, update, or delete, each time you have to create a new assay table with the new information. So actually it's great, but sometimes you don't like to store all this data. So if your disk isn't huge enough, you have to reach your limitation of storage. But with Cassandra, we have an automatic mechanism called compaction, which occurs automatically and reads all this SS table, create a new one, copy the latest value in this new SS table, and remove the oldest one. So that's perfect, that works. But actually, do you remember that we are going to store measurement coming from accelerometers? So if the compaction occurs, we're going to lose a lot of information collected from our accelerometers. That's why we're not going to use this classic way of storage in Cassandra, but we're going to do historical data. So we're going to use time series data model. And for that, the first step to do is to define the 2 properties that are not going to change, the unique properties. In my case here, I can say for each user, I'm going to get the measurement. For each timestamp, I have only a unique measurement for those 2 details. So I can store a lot of measurement using the user ID and the timestamp. And the model will be like this. So I have my accelerometer table containing the user ID, the timestamp, and the 3 forces according to the 3 axes, of course. So my partition key will be the user ID, and my clustering column will be my timestamp. If we have a look to the logical view, so we will have for each user, for each timestamp, the different measurement, of course. But if we look to the disk, we're going to have a row with the test user will be the user ID will be my key, and I have column per timestamp, and for each timestamp, I'll have the different measurement. So I can store a lot of measurement as needed. Another detail about Cassandra, the row has a limitation. And actually, we are storing historical data. So if we store the data, let's say for 3 weeks, we're going to reach this limitation for a row storage. That's why, to avoid reaching this limitation, we can add other information to our model. In this case, for example, we can store it daily, for example. Here, we can keep all the information of acceleration for each user per day, and we have to store the different acceleration information. So here, our primary key became a compound key containing the user ID and the date. So if you have looked to our logical view, we'll see for each user per day, we have the timestamp and the different measurements. And in the disk, how it looks like, we will have a row per day. So per user and per day, we have the different timestamp values and the different acceleration measurements. Another detail about Cassandra, we cannot get all the information at once. We need to have range queries. So here we can only get slices of information from our data. So each time you want to get your acceleration measurement from Cassandra, you have to do the range queries. And of course, another important point, here we are storing historical data. So the most important data is the recent one. So for that, I use the clustering order for my storage to get the recent measurement of acceleration first. Here I used the descent order to get the recent one, of course. But if you don't need to store all the data and to keep it only for temporary, you can, of course, use another way, which is the TTL, the time to live. And when you use the time to live while inserting your information, the data will be available a short time, and then you can do your analysis during this time, and the data will disappear afterward. So here, I showed you how to store the data in Cassandra, how we can do our historical model. The next step will be to analyze it. And to analyze the data, I used Spark. Does anyone know Spark? Use it? Maybe use Spark. Oh yeah, Hugh wants to. So Spark is an open source project too, all written in Scala. It's an open source project supported by Databricks. And Spark is an API built around speed, analysis, and ease of use, of course. So Spark ecosystem contains the Spark core, which is the main project. The Spark core can support a variety of languages like Java, Scala, Python, or R. And there is additional capabilities, other libraries that, came with Spark, which is Spark SQL for structured data, using data frames, Spark Streaming for real-time streaming, MLlib for machine learning algorithm, and graphics to reason and build graph at scale with structured data. So here, with Spark, there is a lot of data sources that came pre-packaged with Spark, like Hive, MySQL, and so on. But for other data sources, we have a point of integration to create our specific connector, like for Cassandra, of course, or Elasticsearch. And Spark works with a very important abstraction, which is the RDD, the Resilient Distributed Dataset. So the RDD represents a collection of objects that can be operated, of course, in parallel. That's why it's fault tolerant. And what will happen with this collection of objects, the RDD, we're going to apply a lot of transformation, and after applying the different transformation, we can apply a different final action and get our result of analysis. So here, just to explain a little bit with the code, I'm going to show you very, very famous, the hello word of Spark. It's called the word count. And in this sample, I want to count the occurrence of words in a text file and only keep the words that occurs more than 3 times. What happens? The first step is to create my Spark context. So here I give the name of my application. I set the manager, the cluster manager. Here it's in standalone mode in local. I initiate my Spark context. I use the Java API here. Then what is the next step is to read my file, to apply to do the first transformation, which is the flat map, just to split the different sentences and get the different word. Here I use space as separator. And after that, I'm going to apply other transformation just to create tuples for each word. Each word is going to have the value 1 in the beginning, and then I can reduce it and have for each word the different occurrences. And after that, I can apply another transformation to keep the words that occurs more than 3 times using filter. And after doing my different transformation, I can apply the action to get the final result, and I can show it or use it for my app. So here, the action is collect. So Spark works with different, Spark context can connect to different sets, different cluster manager. And each cluster manager can allocate the different resources and call the node executor to do the different computation defined in our code. So the Spark context can connect even in standalone mode, so local, as I showed you in the sample, or with Mesos or Yarn. And what we have to remember about Spark is that it is flexible, fast, and very, very easy to start with. So here we saw how to do some computation with Spark and how to deal with some analysis. But what we need to do is to do this analysis in real time. And to do it in real time, we have to combine Spark and Cassandra. And to combine both of them, we are going to use the Spark Cassandra connector. The Spark Cassandra connector is an open source project, all implemented in Scala, that help us load the data from Cassandra into Spark and write the result from Spark into Cassandra. You can find the code of this connector on GitHub. What happens with the Spark Cassandra connector, it's going to expose all the table from Cassandra as an RDD to Spark. So Spark can do his computation and so on. So here, what we're going to change about our configuration with Spark is adding 2 small information. As you see here, it's written in Scala, switch it to Scala. It's pretty the same with Java. So we have only to add 2 information, which are the host to Cassandra and the port, so our Spark context can connect to our Cassandra database, of course. So the first step is to update our Spark context, and then we have to initiate it. And after that, we can read all the information from Cassandra. Here, it's a small sample to read the data from the training table contained in our key space called activity recognition. So I have to call the Spark context functions contained in our connector, the specific connector I used. And this connector is going to read all the table from training and transform it into Cassandra RDDs. So Spark can do the different computation on these Cassandra RDDs. And how it occurs, so here with my RDDs I can apply different transformations, new ones specific for Cassandra, for example here the select and distinct, And we have the usual one with Spark, like map and reduce and so on. We can have a lot of them. And at the end, we can apply the final action, which is the collect action. So here we know how to read it. But to do it in real time, we can't do it with the Spark by its own. We have to use Spark streaming. So Spark streaming helps us create read stream of data, and the Spark streaming is going to read the stream to transform it into batches, and each batch it will be computed by its own in our Spark engine. So we have batch of result at the end. To do it, we have to initiate a Spark context streaming context instead of Spark context, the classical one. And the difference is only with the new parameters you see here. We only have to tell the frequency of our batches. I choose 2 seconds as a frequency to read the data. After that, we have to connect to our receiver. Here for Cassandra, there is no typical receiver that comes prepackaged with Spark streaming. We have to create our own. It's pretty easy. We have only to override one class. I'll show you later. And after that, we have to mention our storage level, of course. So when we get the information from our receiver, we can apply the different transformation needed. Here I'll do different computation needed to recognize my activity. And after that, we have to start only our batches to do the different computation. And as I told you, the Cassandra receiver doesn't really exist, but you only have to override the receiver class and to mention the different type you need to deal with here. And when you override these classes, you have to only override 2 methods, 2 simple ones, the onStart and onStop methods. And for my case, I don't have any specific condition to stop it, so I have only to deal with reading the data from Cassandra in the onStart methods. So now, as we saw how to get the data from the sensor, how to store it, how to stream it and analyze it with Spark and Spark streaming, we're going to do some predictions, so some analysis with this data. And the goal of today, of course, is to try to recognize the different activity which are walking, jogging, sitting, or standing. All this prediction is based on the measurement coming from our accelerometers. So here what we're going to try is to classify the different time series into physical activity classes. And for that, we're going to use machine learning algorithm. So there is a lot of machine learning algorithms. The first one, the logistic regression, which is an algorithm that helps us to classify data into binary result, true, false, success, fail, etc. But if you have to classify like this in multinomial results, you have to do the multinomial logistic regression, which helps us to classify into a lot of results. There is another one called the naive-based algorithm, which is based on different hypotheses. For example, if you have a small object, spheric, red, and a fruit object, you can say it's an apple, for example. But this algorithm is actually outperformed by other algorithms like the random forest. The random forest is a combination of decision trees, and for my presentation, for my prediction, I'm going to use the random forest. As I say, the random forest is a combination of different decision trees based on different features that I'm going to compute. And why I use the random forest, actually, I tried it and I had a very, very good accuracy with my algorithm, so I kept it. And to build my model, I used the Spark MLlib library. The Spark MLlib library came with pre-packaged machine learning algorithm like random forest and the logistic regression too. So here I tried the random forest, and the random forest algorithm is a supervised learning algorithm model. So supervised, that means that we have to train it first and then we can ask him for a prediction. So to train my model, I have computed a lot of features with known activities, for example, here. And after giving him all the features with a known activity, I can give him features without knowing which activity I was doing, and the model will be able to predict the activity. So the step I used to reach my goal is to collect the labeled data, so with known activity, of course, to identify the different features from my data. I computed them, and then I created my model and trained it with this data. And after that, I can use it for my prediction. So the first step I did is to collect the data. And for that, I asked some friends to do the stuff for me. So I asked them to run, to jog, to stay standing for a while, etc., etc. So here are my small control sample I used for my demo. And all the collected data I stored in a new table called training. The difference between the acceleration table and this table that I have a new information, which is the activity. As here, I'm going to store data with known activity to use it to train my model. And I also did another menu in my Android app. You see the second button here to collect the data. You switch to a new screen when you can type your name here. You have a drop list when to select your activity you're going to do. And then when you click to the on the start button, you're going to see the different measurement coming from the accelerometer updated in real time. And all this data are, of course, posted to our server to be stored. So, after storing the different data, I have data like this in my database. So for each user, for each activity, I have the different measurement for this activity. So one more and important detail, as I saw you, only a few friends helped me to collect the data. So here I'm not dealing with the big volume of data, only a small set to do my demo. And the first step I did with the different data I collected is to slice it into windows. So we cannot analyze all the data at once. We have to choose the perfect window size to get the different window and analyze it separately. So here, for example, for my time series, I choose 2 seconds because when I looked to my time series, the 2 seconds period was the perfect one to get the perfect shape of my time series and analyze it. You can, for example, if you have another type of time series, define another window. It's a very, very personal choice. And after that, I have to detect different features from my time series. So here you have two models. The first one is for the time series for standing, and the other one is for sitting. And the time series, as you see, for standing and sitting aren't the same, actually. For example, for the first one, for standing, you can see that the black chart is at the bottom of the others, and in the sitting state, the black chart is above the others. So here, for example, if you'd like to say basically how we can see if we are sitting or standing, we can compute the difference between these two charts, for example, between the Y and the X chart, to see if we are standing or sitting. Here, that's pretty easy to analyze it. So that's the first feature we can compute. But if you look to other complicated activity, like walking or jogging, here, if you focus on the black chart too, you can see when you're walking, the chart is very, very smooth, so the amplitude isn't very important. But when you are jogging, you have a lot of peaks, so the frequency is higher. And here, for example, to say if you are walking or jogging, we can compute the amplitude. So we can see if the amplitude isn't important. We are almost, let's say, if the amplitude is short, we can say we are jogging. If it is bigger, we can say we are walking. Actually, 2 features aren't enough to deal with the difference with different time series. We can add all of other statistical measurement or computation we can do. For example, the average acceleration. We can difference, as I show you, the variance, the standard deviation. We can do the absolute difference also, the resultant, and what I show you, the peak-to-peak amplitude. So here we can see different computation used in statistics. So it's a classy way to analyze different time series. But to do it in our code, what I have to do first is to get different data from my database here and create a vector of data. So why vector? Because here we're going to deal with Spark MLlib, and Spark MLlib have a statistic library to do different computation, and the statistic in general deals with vectors, unfortunately. So here we have to create a vector with our data, and after that we can call the library to do the different statistic computation. So as you see, I didn't implement the formula by my own. It already exists in the statistic, the multivariate statistical summary provided by Spark MLlib. So here we already have the mean, the variance, and a lot of other features. Maybe not all of them, but you can combine the different functionalities already existing there. And after doing all the measurement of the different features, we have to create what we call the labeled point. And the labeled point contains the vector of your features computed and the activity, the label. And all these points that with the known label are going to be used to train our model afterwards. So here you have a collection of labeled points that you're going to use to create your data model, your random forest model. And to create the random forest model, we have a lot of parameters. Just don't be afraid, I only used 2 parameters. All the other values are by default, because I didn't need to, for my case, to do complicated analysis. So here I only choose the number of classes, which are 4. The classes here are according to different activity we're trying to classify in 2. We have 4 activity: walking, jogging, standing or sitting. And here I choose also the number of decision tree I'm going to generate with my model. I'd like to have 10 decision tree for my model. And after that, I only have to call the random forest class already existing in Spark MLlib to train my classifier. I give him my training data and the different values of my parameters. The training data is a set of data already captured, but I use 40% for testing and 60% for training my model. So after training my model, I can measure the accuracy using the remaining set to see if my model has a very, very good accuracy or I have a lot of errors. And of course, we have to save it, so we can reuse it for prediction afterwards. So here, as you see, I have a very, very small set of data for my training. I computed all combined 50 features for each labeled point. And after that, I computed my accuracy. And with this model I already have, I'm going to show you, I have 92% of accuracy, which is very, very good, very high accuracy, actually. So let's move to the demo time. You can tell me if you can see the code. The first step, I'm going to show you my REST server. It's a very, very basic Spring Boot application with one controller when I can post different data from my Android phone here and store it into Cassandra. It's a very, very basic one. I'm going to start, actually. And I don't know if we can share the screen. Up here. Okay, here we go. Oops. It's going to be refreshed. Sorry. Okay. So here I'm sharing my Android screen. Okay, that's the first screen of my phone application. And when we push the start button, we are switching to a new screen here. We are not listening to our sensor, but when I'm going to push my start button, I'm going to put it here, actually. Oops. So here you see the measurement from our accelerometers updated in real time. And in the back, you can see here all the data posted to our server that are going to be stored into Cassandra. So here we are storing the data. I'm going to stop it for a while. And it's not the important part, actually, the REST server. I'm going to show you the machine learning part, which is here. And to do my prediction, so I have here initiate my Spark context with the different information for Cassandra. I started in standalone mode. Initiate my Spark streaming context. Here I changed the frequency to 5 seconds. And if you look to my prediction service here, you can see that I load my stored random forest model. I already created, of course. It took a bit of time to create a random forest model, so I did it before. Here my model, I only have to load it and to use it. And after that, as I show you in the sample, I don't know if you can see everything over there. Here you have the receiver, the Cassandra receiver, to read the different data from my database, and after that, I can apply the different computation here. You can see that I call my feature services with the predict activity, and I'll show you what is the computed feature already over there. So here you can see the different features I'm going to compute. So the mean, the variance, the standard deviation, the average absolute difference, the resultant, the amplitude between peaks, the difference, etc. And afterward, I have all this measurement here in my feature array. So transform it into vector and use it to my prediction. One more important detail is that for prediction, I'm going to use the same order, the same feature I used for training, of course, although it won't work for prediction. And then we can call the prediction service. So here I'm going to start my prediction service. Oop, I put it here and I put the other one here so we can see both of them together. Oops. Here we go. Up. Here. So here you see a Spark running, Spark streaming. Of course, that's why it occurs a lot of times, the logs. And here I'm going to switch up. So here we're going to see the result. This one it has been done lately, actually. But we're going to restart it so we can see the data in real time. I unplug my phone. So here I'm going to restart it to simulate the state standing, of course, for example. So I stand here and we are going to see, no, not working. That's it. He saw the movement from the right to the left, so he thought I was working. No. It's the pretty hardest state to guess each time. Here we go. Come on. Okay. So I'll start working now. Can see? Okay. So I'll go back there and do the jogging because I need a lot of space. Oh, already. Oh no. I'll walk. He's very sensitive today. So if you do the walking. Come on. I can see. No. Maybe jogging the Spanish way, very slowly, I don't know. Walking, okay. So, we're going to jog. Come on. So, oops, I'm going to stop it. Actually, if we change the frequency of listening to the data, we may have more accuracy and so on. So it's a very, very sensitive balance between all the details to have the different information. Let's go back to the slides. Oop. So here, the goal of this presentation, of course, is to show you how we can collect data from our devices, how we can analyze it and use it to do some funny things, prediction, and recognize, for example, the physical activity here. Actually, I used one sensor, and in your smartphone, you can have a lot of sensors. You already have, like a temperature, the gyroscope for the rotation, and a lot of other sensors, so that can be combined, and all the data can be combined to do more funny stuff. So there are a lot of infinite possibility with IoTs. Thank you, and it's time for a question, I guess.
Hello, thanks for the presentation. One question, could you elaborate on why did you choose Cassandra? Star? Did you hear me? Could you provide the rationale of using Cassandra over another NoSQL star?
Actually, I used Cassandra because it fits very pretty to historical data. I didn't use, I use MongoDB for my work today, but MongoDB stores documents and I need to store historical data, and for that Cassandra was the most performant one to store my data. And I showed Cassandra as a solution to store big data volume and to combine it and so on. And actually for my simple, we can avoid using Cassandra and stream it directly with Spark Streaming to do the analysis. The way to use Cassandra was only to show the capability we can use with the database if we need to store other data coming from social media, for example, when you like to store the name of the users and photos and so on. So it works pretty fine with historical data, so that's why I chose Cassandra.
Okay, so that just seemed like a good fit, and you didn't look at other stores. I was just wondering how, if you had any experience with comparing different types of NoSQL stores for this application.
No, I didn't have benchmarking between different databases to see if the best one. Actually, yes, I already used Cassandra for other projects, and with the new features with Cassandra, it was the most. For me, it was the most one to do historical storage.
Okay, thanks a lot.
Yeah. Other questions? So all the code is on my GitHub, of course. You can use it, you can try it, and if you have any questions, you can send me pull requests or any questions on my GitHub account. I'm going to add some good documentation to make the usage more easier. Thank you.